All right, folks, so we have gone through basics of interference, double slit apparatus, thin films, and now we're going to talk about wedges, thin wedges. So how we form a wedge basically is it has something, like you can do it in air, like this, like some sort of piece of glue that you have formed. It has here, let's say, height h and length l, right? And what you do now, this could be like this, it could be sitting in, it could be you formed a thin wedge with two pieces of glass, and these are treated differently. I'll show you why in a bit. Again, this could, let me make it a bit thicker. These are really, really thin pieces of glass, right? So what happens in a simple wedge like this is the following. You got a ray coming down, and again, it's a thin film, right? So part of the ray gets reflected here, part of the ray gets reflected there, and you can view this in reflection, and you can view this in transmission. Let's do an example. Let's take an example. Let's first assign the phases to the phase states to these things. You have phase state of 0, and that's maintained upon transmission. And now let's say that this is some sort of glue of index of refraction, I don't know, say n equals 1.4, okay? This has relevance to the quiz coming up, by the way. So this says 0, 0, 0. We go from 0 to 1.4, from n equals 1 to n equals 1.4. There's a phase shift of phi, and here we're in 1.4 going to 1, no phase shift. This is 0 now, and here we have 1.4 to 1, also 0, 0 again, opposite conditions here and there. Let's say we're looking at this in reflection. In reflection we have 2Tn equals to m lambda, and 2Tn equals to m plus a half lambda. This used to be the condition for constructive, now it is destructive. And this used to be destructive, now it's constructive. Where is T? T is the thickness of the film at a given point. So we're talking about, again, remember, this is not really that widespread, it's near normal incidence, so the ray will be coming up and down like this. So this is the thickness T right here, let's say. Okay, this is your T, okay? And let's see what we can do with this, how far we can take this. So for what thickness so basically here, the path difference between the beams, when you go closer to here, look at the path difference is going to get smaller, because what is the path difference? It's 2Tn. The closer we get to the corner, the smaller the path difference will be, right? Why? Because, you have go down T and up T. Remember, this is in near normal incidence. So if this is the case, then, the closer you get to the corner, the smaller T will be, the smaller the path difference will be. The path difference is delta x. Okay, optical equal to that. Okay, it'll get smaller and smaller until it gets to 0 at this end. And it's interesting to see what happens at this corner here. Right? For now, though, let's see what thickness corresponds to the 7th maximum. Let's say. Okay, let's say I'm looking for the 7th maximum, 7th minimum. Okay, upon transmission. So where is the mth minimum upon reflection? Okay, so that's a problem kind of example. Okay, so where will that be? Well, I'd like to look for the position of that thing. So this is T that corresponds to the mth maximum or minimum, and this is the X that corresponds to where it is along the wedge. So the question is, how far along the wedge, measured from the corner, will the 7th maximum be? So you can see that here I'll get the 1st, 2nd, 3rd, 4th, the thicker the film, the higher the order of interference, right? So what is the mth minimum upon reflection? Upon reflection, we have these conditions. Minima are governed by these, so we need what? 2Tn equals to m lambda gives me the destructive interferences, and that's the minima, right? And that's what I'm looking for. The mth minimum is the mth destructive interference or fringe. So what you'll see here, guys, is at the corner you might have bright or dark, but then as you move in here, the path difference will be equal to lambda. You'll have a maximum or minimum. right? Lambda over 2. Lambda over 2 will give you maximum or minimum. In this case, it's going to give you maximum, then lambda minimum, then maximum, then minimum, then maximum. So you'll see fringes. You'll see lines like that. Okay? Really interesting. There's a thin film of variable width, and what I'd like you to do is on your own. I won't be taking it up with you, but look at Newton's rings. Okay? Look it up. What is Newton's rings? Can you estimate the diameter of the circle in Newton's rings? Newton's rings are, the same thing here, except that you have a bowl of some sort, and you put it on a piece of glass or something, and now this is your interference here, interference space, where the thickness changes, but it doesn't change at a constant rate. It changes at a, the rate is, the slope is variable. What you end up with as you move away, you can end up with here, you might have, depending on the condition, you might have, so looking from the top, you have a bowl, right? You might have a dark spot or a bright spot, and then subtended by rings, right? Dark, bright, whose width changes as we do this for small angles, but you can expect that the distance between the fringes is not going to be the same as what you get here. We're going to look at the interfringe distance in this case here because of the fact that the slope changes as you move out. Right? It's not a constant slope. You're going to see that the width of the fringes, in this case, the width of the fringes is going to be the same. We'll see that in a minute. Here, the width of the rings, call them Newton rings, is going to change is it going to get thicker or thinner? Think about that. Think about what happens to the thickness of the Newton's rings as we go away from the center, and what happens to the spacing between the rings. Right? Here we're looking at so this is T is equal to m lambda over 2n. So let's say I'm looking for T7. For example, T7 would be equal to 7 lambda over 2n. Okay? And remember, m begins at 0, so this is, the 8th one, but we'll call it m equals 7. So 7th is fine too. Okay. So that T, the thickness, where the mth maximum is 0, 1, 2, 3, 4. The mth maximum or minimum happens here. How far is that along the line? That's an important question for us in interference. It's a game we like to play. How do I get this xm? Pause for a second and see on your own, pause for a minute or two, if you can find out what x sub m is equal to. And then on your own, what x sub m plus 1 is equal to. And if you can tell, so you have, this is x sub m, this is the bright fringe here, okay? And the m plus 1 will be here, let's say, okay? That's a bright fringe. What is the distance between them? Can you please pause your video, okay? And actually do the work, okay? Get it done. Find x7 and x8 and what the difference between x7 and x8 will be. All right, folks. From similar triangles, I have that, well, h, look at this, that. So h over L is equal to T sub m divided by x sub m. What is T sub m? I'm labeling T sub m to indicate that it belongs to the m maximum or minimum. So x sub m is equal to what here? L over h times T sub m, and that's equal to L over h multiplied by T sub m is m lambda over 2n. Okay. Now, what x m plus 1 is again equal to, by the same token, T sub m plus 1 L over h into m plus 1 lambda over 2n, and the distance between them, x sub m plus 1 minus x sub m, like what I know, x8 minus x7. Do it with numbers if you like, is going to be equal to L over h lambda over 2n, and we call this the interfringe distance. It's going to be the same between 7 and 8 as it is between, see, because it's m independent, what it's telling you is that 8 to 7 or 10 to 9, 11 to 12, it's going to be the same distance as 2 to 3, 1 to 2, so on and so forth. This is not going to be the same as Newton's rings, so please look that up. One question we have, okay, is what do we do when the wedge is like that? Let's say you have air here, n equals 1, and n equals 1, and n equals 1. How is this going to change the game? And this is glass, so you form the wedge with two, I don't know, two things of laboratory, like what do you call them? I don't know, biology stuff. Anyhow, thin glass things. Okay. This is n equals 1.5, and this is n equals 1.5. Okay. How does this play out here? Well, again, you have to play the game of we draw the ray, okay? And you have to be careful here because you have possible reflection here, possible reflection there. We're only considering, we don't care about what happens between this here because it's a thick, that's a thin film that is, you know, whatever, maybe thin, maybe not thin, but this is not of concern to us. We're interested in the interference between this interface and that interface. So the reflection that we look at is not this one. We look at, this is my thin film right here, variable thin film. One goes here, one goes there. Keep that in mind, okay? And again, this continues through, and this goes down here. So let's do this as an example, basically. What condition am I going to use upon reflection? What condition am I going to use upon transmission? So let's say that this had a phase of 0, and the phase of 0 is continued down, right? You know, in the glass, we have a phase of 0 going from glass to air, no phase slip, that's a 0. Down here we have going from air, we're in air again, so we have air, glass, air, glass, air. 1 to 1.5, this reflects right here, and we have a phase slip of pi, and that phase slip of pi is maintained here because we go from, sorry, this is 0, pi, and then we have pi, something is off here. So we have 0, pi, 0, pi. Yeah, no, we're good. Okay, so this guy maintains its pi on this side, but when it goes from here to there, 1 to 1.5, you have another pi, so you have a pi, and you know, so so this goes, yeah, pi plus pi, so pi plus pi, so it already has a pi, goes from 1 to 1.5, another pi, so that's 2 pi, and that gives you 0, so that's pi plus pi, that's also 0. So you have 0 pi up here and 0, 0 down there. Again, the ray going through has 0, 0, 0 all the way through. Here from glass to air 0, here from air to glass pi, and again from air to glass again, another pi, 2 pi, so we have 0, 0, 0 pi. So upon transmission, let's say, looking upon transmission, what do we have? We have that 2Tn equals m lambda is going to give me what? Think about it for a second. If the thickness is such that 2Tn is equal to m lambda, is this a maximum or a minimum? Because the two have not undergone any phase shift incremental. I mean, we don't have the case that one of the rays underwent an incremental phase shift of pi. They both underwent the same phase shift of 0. Okay? This went from pi to, so we have 0, 0. This will be maxima, if you guessed it right. Okay? So that's how you play with wedges. Okay? We're gonna pause again for the last video in this series, and that'll be end of the week on interference.